So in the introductory movie, I said we'd encountered amines before, not just in the organic modules, but also in the acid-base module. That is because amines are bases. Now, if I go back to the simplest of all amines, in fact, so simple some would say it's not an amine at all, that's in which all the R groups are H's, in other words, ammonia. Well, you've known since pre-GCSE days that ammonia is a base. We bring a water along there. The ammonia says to the hydrogen, I've got a couple of juicy electrons for you here. Would you like them? At which point the hydrogen says yes and tells the oxygen to take its electrons and go away. And so you set up this equilibrium here where you have the conjugate acid of ammonia, ammonium, and then of course there's the hydroxide. That's what's left of the water once the ammonia has snagged one of its hydrogens. So ammonia, of course, we can say that it is a proton acceptor. There's the H+. We can say it is an electron donor. Now, the way, of course, that we describe the strength of weak acids is using Ka. So we would have the same kind of idea here. We would write the equilibrium constant for this particular process as Kb, because this is ammonia acting as a base. And back in the extension for the acid-base topic, lots of extension material where I really talk about Kb's and we do calculations with them and so on. Anyway, the Kb for ammonia, 1.8 times 10 to the minus 5. That's a relatively decent Kb for a weak base. Ammonia is a pretty good weak base. Now, in the same way that the strength of an acid went up when its Ka went up, or a better way to say that is that Ka went up for acid strength going up, Kb goes up as the base strength goes up. Now, back in the acid bases, we talked a lot, not just about Ka, but pKa. So we can talk about pKb as well. And pKb is minus the log of Kb. Remember that little p is minus the log of. So minus the log of 1.8 times 10 to the minus 5 is 4.7. Now, again, you might remember that with acids, as the acid strength goes up, pKa went down. Same thing for bases. The stronger the base, the lower the pKb. And then we also talked back in the acid and base module about the relationship between pH and pOH. Well, it's the same relationship between pKb of the base and pKa for its conjugate acid. Okay, because if this is a base and here's its conjugate acid, this is an acid, can go back to the base. The acid has a Ka and a pKa, and the relationship between pKa and pKb is 14. And all this stuff, of course, dealt with in the acid-base module, some of which in the extension material. So if Kb for ammonia, 1.8 times 10 to the minus 5, pKb, 4.7, pKa, 14, minus 4.7, which is 9.3. So again, if the base strength goes up, the pKb goes down. Well, if the pKb goes down, the pKa goes up. And so the stronger the base, the weaker its conjugate acid, and the higher the pKa of that conjugate acid. Lots of nasty little interrelationships there that are just begging to have you double think yourself, but just look at those relationships there as we're going through it. Anyway, amine, ammonia is the simplest amine, so let's throw a few R groups on there to get our general amine, and it too is a base. There's the lone pair on the nitrogen. The lone pair can do the same old thing with water, blah, 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 giving you its conjugate acid, which would look like this, that is referred to as an alkyl ammonium cation. Now, alkyl ammonium cations, fascinating little topics all on themselves. I'm not going to dwell on them too much. I will point out that years ago, when a student was listening to me talk about amines, we talked about primary, secondary, and tertiary amines. And they said, can you have a quaternary amine? And the answer, you can't have a quaternary amine. But if you think about this cation here, if you instead of having H there, you had another R group, then it would be a quaternary alkyl ammonium cation. But anyway, alkyl ammonium cations for our sake here, all we care about is they are the conjugate acids of our amines. Now let's have a look at a few of these amines in terms of their relative strengths as illustrated by Kb and so forth. So methylamine. Here's the Kb, 4.6 times 10 to the minus 4. It's more than 10 times stronger than ammonia. So that means, of course, its pKb is smaller, and its pKb is more than 1 smaller than ammonia, which means the pKa is bigger, and indeed the pKa of methyl ammonium is more than 1 bigger than the pKa for ammonium. Okay, all of these numbers just the same way, or same thing, saying the same thing, that methylamine is a stronger base than ammonia is. Now, why is that? Why is putting a methyl group there going to make the base 10 times stronger? And the answer lies in the old inductive effect. Alkyl groups have a positive inductive effect. In other words, they push electrons towards the nitrogen. Now, if they push electrons towards the nitrogen, that means that this nitrogen now has got more electron density. And of course, if it's got more electron density, it's easier for it to donate those electrons. And the ease with which it donates electrons, its ability to donate electrons, is the very heart of its basicity. So the easier it is for the nitrogen to donate electrons, the stronger a base it is. Thus, only hydrogens here, no inductive effect at all. Start sticking in groups that have a positive inductive effect, and you're making it easier for the nitrogen to donate its electrons. You're making it a stronger base. Now, if I expand this table a little bit, I want to make 2 points. The first is that as we go from methylamine to dimethylamine, it gets even stronger. 4.6 times 10 to the minus 4 going to 5.3 times 10 to the minus 4. So the more methyl groups, the more alkyl groups generally you have, you would imagine, and it's generally true, the stronger the base you're going to have. But do notice, and this is the second point I wanted to make, it's not a huge lot of difference here between methyl, ethyl, dimethyl, and diethyl. Obviously, these are stronger bases down here than up here. But the gap between having no alkyl groups and having one alkyl group, in other words, between ammonia, let's look at the pKa, the ammonia, 9.3, put on one methyl group, you jump up by 1.3. You don't see that same jump as you keep adding on alkyl groups. In other words, what's important is you have an alkyl group there at all, not necessarily which alkyl group it is. Now, if adding alkyl groups onto the nitrogen with that positive inductive effect makes it a stronger base, what happens when we start sticking on some electron withdrawing groups, ones with a negative inductive effect? And the answer is it's actually really tough to come up with some good examples for you, because a lot of the good examples you might think of are either unstable anyway, like for example, instead of ammonia, try NCl3, or else they've been made or maybe not made, but their KBs haven't been measured. One I could find though, that we've already mentioned, is where you have an OH group up there, so the 2-amino ethanol. Okay, put this OH group here. Well, of course, O has got negative inductive effect. It's sucking electrons away. So in the same way that if something's pushing electrons towards the nitrogen, it makes it easier to donate. When you have an electronegative group, it's going to suck electrons away from the nitrogen, making it harder to donate. And if it's harder for it to donate, it becomes a weaker base. Now, this species here with the OH there, so the 2-amino ethanol, is a much weaker base than ethylamine, which is the best comparison here. Here you've only got alkyl groups. Here, replace one of the hydrogens by an OH. As soon as you do that, you drop the basicity by 1/1 unit again, going from 3.35 to 4.5. So having the alkyl group there, the 2-amino ethanol, much weaker base than ethylamine because of the electron withdrawing properties of the OH. So basicity behaves in a way similar as you would expect, but opposite to the strength of acids. What we're looking at here is how easy is it for this nitrogen to donate that lone pair of electrons. The more electron density that's pushed onto the nitrogen, the easier it is to donate those electrons. We spent a lot of time in this course talking about how electronic effects, that's inductive effects, resonance and so forth, affect acidity, basicity, reactivity, stability, and so on. Now, once you get into the broader area of organic chemistry, electronic effects are extremely important, but you will also often see so-called steric effects, how the size of something affects a particular property, whether it be acidity, reactivity, and so forth. We have mentioned it once or twice before, but it certainly hasn't been a dominant consideration. Well, it's worth just noting here on a very fast slide that you can see some of these steric effects affecting basicity. If I just look at the nice little series where we go from methylamine to dimethylamine to trimethylamine. Well, of course, we've said when you've got an alkyl group, you push electrons towards the nitrogen, making that nitrogen happier to release the lone pair of electrons. So one methyl group will make it stronger than ammonia. Two methyl groups will make it even stronger. Three methyl groups should be much stronger. Well, if I look at the K values for this, we don't see that trend. We see it initially as we go from 1 methyl to 2 methyl. The Kb goes from 4.6 to 5.3, both of those times 10 to the minus 4. The pKb gets a little bit smaller, as you would expect, because the base is getting a little bit better of a base, going from 3.34 to 3.27, and then the pKa 10.66 to 10.73. So you'd expect when you put that third methyl group in here, it will get a little bit better. So maybe this would go, instead of 4.6 to 5.3, maybe this would be up there at about 7 times 10 to the minus 4. Or maybe this would be at about 3.2, and this would be up at about 10.8. Well, what we see is that there's a significant decrease in the basicity. We go from 10 to the minus 4 to 10 to the minus 5. So a tenfold decrease in the basicity. This leads to an increase in 1 in the pKb and a decrease of 1 in the pKa. Why suddenly has throwing in that third methyl group made it a weaker base? And the answer is steric. If we're going to make this a base, have it act as a base, it's going to have to stick a group on here. Okay. Now, of course, electronically, we say no problem sticking a group on there. But you put a group on there, and it's going to have to force these methyl groups to get a little bit closer to each other than they are comfortable with. Having two methyl groups, no problem. One methyl group getting close to hydrogens, well, it relishes it. Three methyl groups having to get close to each other, there's just not quite enough space for them to get so close to each other. As there's not as much space, no matter how much the nitrogen wants to give away its lone pair of electrons, the methyl groups are saying, don't crowd us, please. So therefore, for steric effects rather than electronic effects, trimethylamine is a weaker base than dimethylamine.